All right, welcome to the third video for lecture for chapter 2. In this video, we are going to talk about using the standard deviation of a data set to compare, using standard deviation to compare data sets and to find extreme observations. So remember that the standard deviation is a summary statistic that tells you about the spread of data. A larger standard deviation means the data is spread out more. And that's nice because you can compare data sets that maybe don't have the same sort of shape or in a variety of ways don't look super similar, but you can still figure out which one of them is spread out more. So I'm going to hop over to R and show you some examples of that. I'm going to create two data sets. Of a size 100 each. All right, so let's look at each of these data sets using a histogram. So let's use a histogram of data 1. I don't know what to do. Because as I said in an earlier video, visuals are my favorite way to explore data. There's a histogram of data 1. Okay, I can quickly see that the smallest value is going to be around 3. The largest is around 12. So the range is going to be about, what, 9? And it seems to be centered somewhere in 7 or 8. No outliers. Seems to be kind of some more data in the middle versus on the ends. And let's look at data 2. All right, so here I can see that the data seems to be spread between 5 and 9. The center still looks like it's around 7. If I wanted to get some 5-number summaries, I could look at the box plot of data 1. Yeah, pretty symmetric, right? These whiskers are about the same size. Each size of the box is roughly the same. This data is also symmetric, but the boxes are bigger, but they're still like the left side and the right side are roughly the same size. The whiskers are roughly the same size. So flipping back and forth between these two box plots, it looks like data 1 has a bigger spread than data 2, which I can do with the visual analysis. And a standard deviation lets you do that using single numbers, using that summary statistic. Standard deviations don't mean much without including also the measure of center, in this case, the mean. So let's look at the mean of data 1, the mean of data 2, the standard deviation of data 1, and the standard deviation of data 2. So the means are close to each other, 7.7 and 7. But the standard deviation of my data 1 set, 2.3, is about twice as big as the standard deviation of my data 2 set. So data 1 is spread out more than data 2. That's the first use of standard deviation, is to compare which data sets are spread out more. Let me put this. The other use is finding extreme observations. So mathematically, about 95% of observations of any given data set will be within 2 standard deviations of the center of the mean. So if you did have a histogram of your data and you looked at where that data is, 95% of those observations are going to be less than 2 standard deviations from the center. Let me show you that in R. I'm going to come up with another data set, call it data 3. Give it plenty of observations. All right, looking for extreme observations. So there we have our data set. Let's look at a histogram. This one's roughly bell-shaped. And the reason it's bell-shaped is I asked R to give me observations from a bell-shaped distribution. And if we look at our standard deviation, what's our standard deviation of data 3? It should be about 5. So this means that, oh, and what's the mean of our data? Mean is 20. Standard deviation is about 5. So mathematically speaking, I would expect almost all, which in this case is 95%, of the observations in the data set to be within 2 standard deviations of the mean. In this case, almost all of the observations should be within 10 of the mean, right? 10, which is 2 times 5, which should be within 10 units of the mean, which is in 20, which equals 20. So almost all of the observations should be between 10 and 30. If we look at our histogram, we could see that almost all of our observations are between 10 and 30, exactly what we would expect. Any observation more than 2 standard deviations away from the mean is unlikely. Right? There is a less than, mathematically speaking, there is a less than 5% chance that an observation will be more than 10 units away from the mean, more than 2 standard deviations away from the mean. So we can see we do have a couple, right? So we've got some extreme observations on the lower end and extreme observations on the upper end. So the main reason we calculate that standard deviation is to figure out where our cutoffs are for our extreme observations, or to figure out how extreme an observation will be. I'm going to pause real quick and do some formatting that you don't need to. Okay, so let's suppose we have an observation that equals 12. How extreme is this observation? Well, in statistics, asking how extreme is this observation, is the same thing as asking how many standard deviations away from the mean is this observation. So I want you to keep that in mind. Whenever we talk about extreme or unlikely, we're talking about how many standard deviations away from the mean is this observation. To figure this out, we use a simple arithmetic. We use simple arithmetic. We take our observation, we subtract the mean, and we divide by the standard deviation. So in this case, we take 12 minus 20 and divide by 5, which is negative 1.6. So the observation observation 12 gives us a result of negative 1.6. The name for this is called the z-score associated with the observation. Don't worry about why it's called the z-score, it is. Negative 1.6 means that the observation 12 is 1.6 standard deviations below the mean. It's below because it's negative, and the 1.6 tells you how many standard deviations away it is. This is not very extreme because it is less than 2 standard deviations away from the mean. What about the observation 33? So let's find the z-score. We take 33, subtract 20, and divide by 5, and we get 2.6. This means that the observation 33 is 2.6 standard deviations above the mean. It's above because it's positive 2.6, which is extreme. Right, we would not expect to see an observation of 33 in our data set very often. Certainly it's going to happen. Here's our histogram, and we can see that 33 exists sometimes, but it's not very common. It would be surprising if we had that observation. As a statistician, we are looking for surprising results. This is something I want you to keep in mind throughout the whole course. What we are really looking for are surprising results. That is observations that we would not expect to see if the world were boring. Let me give you an example. This is the example I like to use to explain this idea. Actually, before I do that, because statisticians are mathematicians, we decide if a result is surprising or not by using mathematics. Potentially misspelled. That looks good. That one's wrong. Statistician. Okay. So statisticians got it. Almost. Got it. Okay, so as a statistician, we are always looking for surprising results. We're looking for observations that we would not expect to see if the world were boring. And because statisticians are mathematicians, our decision criterion, if a result is surprising or not, is mathematical in nature. Here's the math. 33 minus 20 over 5 equals 2.6. To a statistician, that means, that's surprising. Here's the math. 12 minus 20 over 5 equals negative 1.6. That's not surprising. This can be one of the most challenging pieces of statistics, especially when we get to hypothesis testing and the wording is very strange. So my example that I encourage you to keep in mind comes from The Wizard of Oz. Dorothy lives in Kansas, which is black and white. Oh yeah, that's boring. That's boring to us, right? Um, one day a tornado hits and Dorothy is whisked off to a colorful land with bright flowers, a yellow brick road, and ruby slippers on her feet. If you watched the movie recently, you might remember she says to her dog Toto, "I don't think we're in Kansas anymore." That's a statistical conclusion. Why does Dorothy think they're not in Kansas? Because in Kansas, where everything's black and white, and she lives on a farm, it's very unlikely that she would be in a colorful land with bright flowers, a yellow road, and ruby slippers on her feet. The ruby slippers are strong evidence that she is not in boring old Kansas anymore. Now, I don't actually think Kansas is boring, but from a statistician's point, Kansas is where we would expect to be. But now we have evidence to think, well, we're not in Kansas anymore. Now, let me give you an example from maybe back in the statistics world a little bit. You gather a group of people together and measure all their heights. The average height is, let's say, I'm going to do this in inches, 68 inches. That's 5 feet 8 inches. The standard deviation of the heights is 3 inches. This means that you would expect every person to, or sorry, not every person, 95% of people to be within 2 standard deviations, 6 inches of the average, i.e. between 5'2" and 6'2", I believe. Yep, 5'2" and 6'2". Now LeBron James shows up. Is that a surprise? Probably in more ways than one. LeBron James is 6'8", so his height is extreme and unlikely to observe in your sample. Okay, so this concludes our video. As a recap, the standard deviation is used a lot in statistics. One way it's used is to compare data sets to see which one is more spread out than the other. And I should, in fact, say that. Notice that the standard deviation of data one was what it was. Let me hop back over. 2.34. And the standard deviation of data two was 1.23. So data one is spread out more than data two. That's one of our uses for standard deviation of data sets. The more common use is to find extreme observations. So once we have a data set, we can calculate the mean and the standard deviation. In this data set, the mean is 20, the standard deviation is 5. That means almost all of our observations should be between 10 and 30 within 2 standard deviations of the mean. So if we found an observation of, say, 33, that's 2.6 standard deviations away. That's an extreme observation. This is mathematically unlikely. Statisticians are always looking for surprising results, observations we would not expect to see if the world were boring. And because we're mathematicians, we use math to decide if a result is surprising or not. But we don't have to use math. Really, you can use this process with any type of logic. Like in The Wizard of Oz, Dorothy, who lives in black and white Kansas, wakes up one day with ruby slippers on her feet and says to Toto, I don't think we're in Kansas anymore, because she would not be wearing ruby slippers if she were living in black and white Kansas on a farm. In later classes, we're going to actually put probabilities. So we don't just say that's extreme and unlikely. We can say, what is the exact likelihood? What's the chance or the probability of observing that observation? How likely would it be for LeBron James to actually show up to be counted in your sample? Well, that's maybe a 1 in a million chance, right? So we can put actual probabilities on that. But for now, and in fact, through the whole course, what I really want you to keep in mind is if we look for evidence and we find extreme observations, however we decide an observation as extreme, if it's because it's more than 2 standard deviations from the mean, if it's because it's ruby slippers, if it's because it's LeBron James, if we see something that's extreme, that gives us evidence that we are not in a boring world, which is ultimately the goal of a statistician. Thanks for watching this video. This concludes Chapter 2 lecture. And I will, in the coming days, post the next set of videos for Chapter 3.